Now let's look at a sample problem involving the concept of the center of mass and the conservation of linear momentum. In fact, these two things are somewhat related. That's what we put in the same chapter. Imagine a flatbed car that can roll back and forth on a frictionless horizontal track. Okay, the length of the flatbed car is L. From here to there is L, uniform distributed, and the total mass is capital M. Now, a person starts from the left end of the car and he walks to the right end. He stops at the right end. Okay, now, since this thing, railroad is completely frictionless, as the person walks forward, he's going to have to push the car backwards, so the car ends up going backwards, right? So the car ends up moving backward by distance x, while the person walks forward over the length of the car, so he ends up at this location. So this is the initial, this is the final. I'm not going to tell you how fast the person walks. I'm not going to tell you whether he slows down or he speeds up. All I want to know is if his mass is small n, by the time he reaches the other end, the right end of the flatbed car, how far has the car itself retreated backwards? That is, what is x equal to? Okay, don't try to figure out this problem by applying Newton's second law to this person, because you have no idea what's the force between him and the flatbed car, which of course is friction force on his feet. You don't know whether he speeds up or slows down. You don't know anything like that. You don't know how long it takes for him to go there, right? So that is obviously not a good idea. So what do we do? Well, let's have this in mind. Let's be very conscientious about conservation laws. You know, if I consider the person and the car as part of the same system, then isn't it true that the force between him and the car is an internal force? However complicated it is, right? It's internal force. Internal force will not affect what? Will not affect the center of mass motion, does it? It will not affect the center of mass motion. Okay. In fact, you look at the horizontal or x direction. In that x direction, for the car and the person as a system, is there any external force whatsoever on that system? Well, no. The only possibility is friction, but it does not exist. Okay, so there is no external force. F net x is 0, which means the center of mass cannot accelerate in the x direction. Now, if the person starts from rest, then at t equals 0, when he starts from rest, what is the acceleration of the center of mass at that point? What is the velocity of the center of mass at that point? That will be 0 because neither him nor the car is moving, right? The center of mass of the system is not moving at all. And since the net external force on the system is 0, ACM is also 0, which means the center of mass cannot accelerate. It cannot change its velocity. The velocity was 0 to begin with and cannot change, which means the velocity is always equal to 0, no matter how the person or the car moves. The center of mass of the system can never shift. It is pinned. It is fixed. Okay, there we go. We found an equation. What equation? The initial position of the center of mass equals to the final position of the center of mass. It's just that simple, right? Okay. That can allow us to figure out what x is. Let's do that. Okay, let's choose a coordinate system originate here. Okay, at the initial position of the person is also the left end of the car. Where is the center of mass of this initial position? Here's initial and here's final. For the initial position, the system is made of two parts, the person and the flatbed car. Being uniform, the center of mass of the flatbed car will be right in the middle, half of L from the origin. So I have XCM initial equals to M1 X1, that's M times X1 for the person, that's 0, right? His initial position is 0, plus M2, that's capital M, times its center of mass position from here to there, that is L over 2, divided by the sum of the two masses. And what about the center of mass final position, XCM? Final position. What is that equal to? Okay, again, here is our origin, right? So, is the center of mass of the car still here? No, the whole car has moved leftward by distance x. So the center of mass of the car is no longer at L over 2 anymore. Rather, it's L over 2 minus x, right? It's L over 2 to this one, you go back by x. So the contribution from the cart is now m times L over 2 minus x, right? What about the person? Well, the person is now here, right? Okay, this distance is L, but then the cart moved backward by x, so he ends up at actual distance L minus x from the origin. So it's m times L minus x. That's the contribution from the person. That's from the cart, divided by the total mass. Right? Okay. Initial position of center of mass, final position of center of mass. How are they related? Remember I said the center of mass was not moving, and it cannot possibly start moving because the acceleration remains zero because of the lack of external force. So the center of mass, initial, final position are the same. It can never move. There we go. We equate these two, and we can solve for x. And here's the simple solution after you equate these two. The distance the cart retreats equals m mass of the person divided by the total mass times L. Let's look at a couple of special cases. Okay, first of all, if the cart is a lot more massive than the person, the cart is extremely heavy, the person is very light by comparison, then as the person goes forward, what happens to the cart? The cart being so massive doesn't care, right? It doesn't want to move, right? The cart stays, so what's x? X should be roughly equal to 0, and that's exactly what I'm looking for here. Capital M is much greater than small m, so it's almost equal to 0, okay? It hardly goes backwards. On the other hand, if the person is far more massive than the car, then as the person walks forward, the car will have to go all the way backward. In fact, if the person is far more massive than the car, then the center of mass of the system is pretty much the center of mass of the person, and that center of mass cannot move. You remember? It cannot move. So the person eventually ends up not doing anything, not moving forward or back relative to the ground, which means he stays there. Even though he ends up at the right end of the car, that means the car has to retreat all the way back by distance equal to L. So x would be equal to L. The person will end up at the same location relative to the track. And that's exactly correct, because when small m is far greater than capital M, this ratio is almost equal to 1, right? So x is roughly equal to L. So it all makes sense. And this is how we exploited the fact that the center of mass cannot accelerate. So it's an important application of the center of mass. You can also do this problem using the concept of conservation of linear momentum, because after all, the force between the person and the car is internal, so therefore, due to the lack of external force in the horizontal direction, for the system, the linear momentum is conserved. Okay, the linear momentum is conserved, so I can say the linear momentum of the person must cancel with the linear momentum of the car, because initially they have no linear momentum. Okay, so the person goes forward, m v1, the car goes backward with the linear momentum capital M v2. That's when they start moving. Okay, before they move, neither of them has any linear momentum, so the linear momentum system is 0, so P initial is 0. P final equals mv1 minus capital M v2. These v1 and v2 are positive, they're all magnitudes. That's why I attach the negative sign here to account for the direction of motion. Okay, P initial and P final are the same, right? Because after all, the momentum is conserved. So that tells you that m v1 equals capital M v2. And we're not looking for v, are we? We're looking for this distance the cart has moved. The car has moved. You're looking for the time integral of v2. That's what I'm looking for. v2 is the speed of the car measured from the ground. We're looking for x, which is v2 dt. That's what we're looking for. So what we need to do is we integrate over both sides. Okay, we need to integrate over both sides. So here if small m v1 dt equals capital M v2 dt. Okay, now what is v2 dt? v2 dt, if we integrate over time, that's the distance the car travels, that's x, right? What about v1 dt? Be careful, this v1 is measured relative to the road, right? not relative to the car, because V2 is also measured relative to the road. This V1, V2 are both measured relative to the road. So this V1 dt is the distance traveled by the person relative to the road, not to the car. The person went from here to there. This is the distance he traveled, L minus x. So this is L minus x. Okay? So I conclude that m times L minus x equals the mass of the car, capital M, times x. And that will give me the exact same result. X equals to m over sum of the mass times L. I get exactly the same result as that. Okay, the concept is a little different, but they're related. What we did here was we started with conservation of linear momentum, so we related the two velocities, v1 of the person going forward and v2 of the car retreating. And then we realized it's not the velocity we're looking for directly, we're looking for the distance covered. So we have to integrate over time, and this is x, this is L minus x. We get the same result. Finally, let's look at the case if the mass of the system can change with respect to time. Is it true that F still equals ma? Well, in the beginning of the lecture, we realized that something could be wrong with it because a rocket in the middle of nowhere, there's absolutely no force exerted on it because there's nothing nearby. Yet it can still accelerate, it can even still make a turn. How does it do that though? Well, it has to burn fuel, right? And as it burns fuel, what happens to the massive rocket? It is decreasing, okay? And the fuel is not just burned, rather it is being accelerated back, rushed backwards. As a result, the rocket goes forward. And that makes perfect sense. Why? Because if you look at the rocket and fuel as a whole system, that system, of course, is totally isolated from the rest of the universe. There's nothing close by, so the net force, external force on the system must be zero, right? So this rocket is only part of the system. The fuel is the other part. Now, the momentum of the combined system, fuel plus the rocket, cannot change because of conservation of linear momentum due to the lack of external force. So as the rocket accelerates forward, it acquires greater momentum forward. How does that balance out the momentum? Well, the fuel is now being accelerated backwards. Okay, so you have a increased forward momentum balanced by an increased backward momentum. The total momentum still remains the same. So that makes sense. Okay, but if I focus your attention only on the rocket, whose mass is decreasing, you find that despite the fact that the rocket is not subject to any external force from, say, a star or planet, whatever, it can still accelerate. F is not equal to ma anymore because F is, there's nothing close by. F is 0, but A is not 0. But don't forget, that is because the rocket is burning fuel. In fact, m is decreasing. You know, when an airplane flies, of course, its mass is also decreasing because of the fuel consumption. But that's nothing compared with a rocket. In the case of a rocket, over 50% of its mass can actually be just the fuel. So after the fuel is all gone, the rocket will be more than 50% lighter than before. So we have to consider the reduction in mass. So how does one work out Newton's second law in its most general case? Well, you still can use conservation of conservation momentum for the entire system, but F is no longer equal to ma when the mass changes. You can still use conservation momentum. Momentum is conserved as long as there is no external force. If there is an external force, F external, momentum will change. How does it change? Well, the external force equals the rate of change of linear momentum. We learned that that's equivalent to the work to the Impulse-Momentum Theorem, right? dP equals F dt. The difference was that before, when we wrote P as mv, we never considered m to be a changing quantity. We thought it was a constant. That's why m can be taken out, and what you have left is dv dt, which is a. But what if m is not a constant? It turns out dp dt is still equal to f. But when you write f equals p equals mv, when you work this out, you must consider the fact that m changes. So it's like d dt of ab, right? How do you do that? It's a dv dt plus b dA dt. Remember the calculus formula? So the first term is simple. I take that m out. I get dv dt, which is a. It's just f equals ma. But there is a second term now. Okay, there's a second term. And what's that? That's v dm dt. Look at that. This is the term that only exists when there is a changing mass. Okay, dm dt, when the mass changes. And let's apply this to the case of a rocket. In the middle of nowhere, what's the external force again? 0. Okay, there is no external force. So, does that mean A is 0? No, it means A, ma plus this term is equal to 0. All right, what's dm dt? Is it positive or negative when a rocket burns fuel? Well, the mass decreases, right? So dm dt is less than 0, which means this second term is opposite in direction to v, because it's v times a negative quantity, right? Okay, remember, A, this first term plus the second term equals 0 because there's no external force. Okay? Doesn't that tell you that this first term and the second term must be in opposite direction? Because they add up to 0, right? But the second term is opposite to v. That means the first term, A, must be in the same direction as v, which means the rocket accelerates, goes faster and faster. I can write this explicitly. So if f external equals 0 and dm dt is less than 0, so that's the case of a rocket, okay, burning fuel, then I can write 0 equals ma plus v dm dt. So I have ma minus v dm dt equals 0. Let me explain to you why is that. First of all, it's 0 because f net is 0. And why is the negative absolute value dm dt? Because dm dt is a negative quantity. That's why I can write this. So let me solve for a now. A equals to 1 over m, absolute value of dm over dt, times v. Indeed, you see, a equals something positive times v, which means a and v are in the same direction. The rocket ends up accelerating forward. Okay, so when the mass is not a constant, we got to consider this effect, dm dt, which can cause an acceleration on an object even in the absence of external force. As an interesting application of the formula f equals dp dt, which is more general than f equals ma, let's consider this problem of a falling chain. Suppose there is a uniform chain of length, flexible uniform chain of mass m and length l. What you do is you hold the chain so that it's right above a scale. The bottom of the chain is barely touching the scale, so the scale of course reads 0. Okay, and then what you do is let go of the chain, let it fall, okay, onto the scale. And the question is, if at the moment when the top of the chain has fallen the distance x, which means this part, the same length x, is now on the table, on the scale. At that moment, what does the scale read? What's the reading of the scale? Okay, you might think that the reading of the scale is equal to the weight of the part of the chain that's already on the scale, and that part is simple. Okay, that's the mass of that part times the acceleration gravity. So let's call this force W. That's the weight. W equals to the mass of the part of the chain m prime, then times g. Okay, what's m prime equal to? M prime equals x over L, that's the fraction, times the total mass. That's the mass of the part of the chain that's already on the ground, and on the scale, times g. Is it true that this is the weight? This is the reading? Well, that's only part of the reading, as a matter of fact. Okay, that's the interesting part. The other part comes from the fact that the scale has to give an upward impulse to slow down a certain segment of the chain that's right falling onto it. This red segment that I highlighted, it was moving with a speed v, but a time dt later it is no longer moving anymore. Somebody must give it an upward impulse to bring the speed down to 0 from v, and that upward impulse comes from the scale. So the scale has supported with an extra force beyond that. Okay, so what is that extra force equal to? Let's consider this extra force needed to bring this chain, the second chain, from speed 0 down to speed from speed v down to speed 0. That's called f prime. dp over dt, right? That's the formula we use. Okay, what's dp? Well, you consider a little segment of the chain. This segment, before it falls, it has a mass dm, and the speed was equal to v. And after it falls, the speed reduces to 0, so the absolute value of dp is dm times v. Okay, I'm just looking at absolute value here. Everything is absolute value. And now I divide it by dt. What's dm? dm is the amount of the mass of the chain that falls onto the scale over a time dt. Okay, everything happens in time dt. So what is dm over dt? Well, let's say over a time dt, how far has the chain fallen? It follows by distance dx, right? So dm is really just the mass of the chain whose length is dx. All right? So what is that equal to? Now, isn't it true that dm over m equals dx over L due to the fact that the chain is uniform? Okay, so I can write this as dm equals m dx over L times v divided by dt. dx over dt, that's a v itself, that's m over L, v squared. What is v? V is the speed of the dangling part of the chain after falling distance dx, and that's a free fall, right? The top is doing a free fall, so we have v squared equals 2gx. You plug that in, f prime equals 2gxm over L. You add that to w, that's the part of the weight of the chain that's already on the scale, you get a total force. And in fact, f prime turns out to be always twice the weight of the chain that's already there. You add f prime and w together, you get 3mgx over L. And that means when the entire chain is falling on the ground at that very moment, the thing has to support 3 times the weight of the chain. And that is really remarkable.